Good day today. Today we will see on the last component which we have listed as the devices for efficient power conversion. We had seen in the earlier lectures the other devices, namely the switches, inductors, transformers and so on, and the lossless electrical circuit element which is still remaining to be covered in our lectures is the capacitors, and that is the fourth component, fourth device which are used in efficient power conversion. So, in this lecture we will try to see the basic properties of capacitors, different types of capacitors available, how does one understand the process of energy storage in the capacitors, how do we specify them, how do we test them and so on. The switches we had seen in the first set of lectures are used in efficient power conversion for the purpose of control. Control and flow of energy is being carried out by the presence of switches. And we had seen that the inductors could store energy and smoothen the flow of energy in power converter circuits. The transformers we saw were used to match voltage levels to step up voltages or step down voltages to give electrical isolation and so on. The last element that we are going to see in this set of lectures is the capacitors. Capacitors store energy and their purpose is also to smoothen the flow of power from the source to the load. The switches which are used in power converters necessarily introduce discontinuities in the flow of power, and the energy storage elements, which are the inductors and capacitors which are used in power converters, are used mainly for smoothening the flow of power. These are energy storage elements. The capacitors store energy just like inductors. The capacitors also can store energy. The energy stored in the capacitor is in the form of an electric field. We saw that the inductors were storing energy in the form of magnetic field. In the capacitors, the storage is done in the form of electric field, and in power converters, in order to smoothen the flow of energy from the source to the load, capacitors are used for that purpose. Capacitors are also used in protection circuits. The switches we had seen that are subjected to large voltage and current stresses, and it is necessary to protect them against over voltages and over currents during switch on and switch off. We had seen that during switch on, over currents are prevented by introducing inductors in the circuit, and inductors by the nature of their capacity to limit the di by dt, the rate of rise of current, provide protection against turn on process in the switch. In a similar way, capacitors are used as switching aid elements in order to provide protection during the turn off process. This protection is to prevent very large over voltages occurring in the circuit, much more than the supply voltage. The capacitors are able to suppress over voltages. In that capacity, in many power converters, capacitors are used as switch protection element. We have seen two functions. One is to smoothen the flow of energy, and the second one is to protect the devices during the turn off process from over voltages. The capacitor is a circuit element, and as a circuit element, it can be defined through the voltage across the capacitor V and the current through the capacitor I, what you see here as V and I, and the relationship between the current and voltage can be expressed in the form of a differential equation or in the form of an integral equation. The first one relates the current to the rate of change of voltage. The current through the capacitor is capacitance times the rate of change of voltage across the capacitor. The inverse relationship of this is that the voltage across a capacitor is equal to Vi, the initial voltage at any instant t equal to 0, plus the quantity of charge that is supplied to the capacitor divided by the value of the capacitance. So, this relates, given the current function and the initial voltage, it is possible to find out the voltage across the capacitor. And in the other equation, current to voltage, if we know what is the voltage that is applied across the capacitor, it is possible to find out the current through the capacitor. These are the circuit equations, and these equations are the ones which we use in order to develop several design relationships. The capacitor accumulates charge in order to store energy. The integral form of the equation between V and I in the capacitor is restated here. The voltage across the capacitor as a function of time is the initial voltage Vi plus the charge that is supplied to the capacitor divided by C. Integral 0 to t I dt is nothing but the total charge that is supplied to the capacitor Q. So, we see that the voltage across the capacitor is the initial voltage plus the charge supplied in any time divided by the value of the capacitance. So, you can see that this relationship indicates that the capacitor is capable of accumulating charge in order to store energy. The charge is accumulated on the plates of the capacitor and it appears in the form of a voltage, and a charged capacitor will have a certain voltage, and the stored energy is related to the voltage and the capacitance. When we use capacitors in a periodic circuit, in an AC circuit or a periodic circuit, what we notice is that the voltage across the capacitor will be a periodic function. V of t is V of t plus capital T, where capital T is the period of the circuit. And if this is true, then over one cycle, from t to t plus t, over one cycle, whatever is the charge that is accumulated by the capacitor has to be 0, because at the end of the cycle the voltage remains the same as it was before, and the result of this, the consequence of this is that in a periodic circuit one can use the relationship that in one period the charge that is accumulated on the capacitor is 0, or in other words, the integral of I dt or ampere second, this is also mentioned as ampere second integral over one cycle, and that is 0. Many times this relationship is useful in order to find out several steady state performance figures for a capacitor in any typical switching circuit. In periodic AC application, the net charge accumulation per cycle is 0, which is another way of stating that the under periodic conditions, every cycle the voltage keeps on repeating the same as the previous cycle. The relationship in a periodic circuit, I have drawn a typical periodic current and voltage across a capacitor, where the time function of voltage is a periodic function. What you see here, it keeps repeating every cycle. There is a ramp up of the voltage and a flat voltage, constant voltage, then ramping down, and then some kind of a sinusoidal voltage on the capacitor in the reverse direction, and then no voltage for some duration, and then the cycle repeats. This could be a typical voltage waveform on a capacitor. The relationship of V equal to C dV by dt can be seen here, that during the ramp time, when the voltage across the capacitor is increasing linearly, you will see that the capacitor current is constant. C times the slope here will give the positive charging current on the capacitor. During the time the capacitor voltage is constant, we find that the current here is 0, and during the time when the capacitor voltage is linearly falling down to 0, the capacitor is discharging, or the current through the capacitor is negative value of constant magnitude, and during the time when there is no change in the capacitor voltage, the current in the capacitor is again 0. The sinusoidal voltage change in the capacitor voltage will have a cosinusoidal current change, because the current is the derivative of the voltage. You see that a large negative slope here results in a large negative current in the capacitor. As the capacitor reaches a peak value here, at this point dV by dt is 0, the current is 0, and as the current is charging back to 0, the positive slope here corresponds to the positive charging current here, and then the cycle repeats. The capacitor current in any circuit is proportional to dV by dt, and that proportionality constant is the value of the capacitance. It is possible in many situations from the sketches of the voltages to draw the sketches of the currents, and if we know the mathematical relationship, it is possible to differentiate it and get the current values. Now, in a periodic circuit, we had seen that there has to be charge balance, and what we see here from this instant to this instant over one cycle, there is no net change in the voltage. Whatever was the voltage at this point is the same here. So, the voltage that was lost here during this part is gained here. So, the net voltage drop is the same as the net voltage rise, and voltage drop is equal to the charge that is taken away from the capacitor. What you see here as the areas indicated by the negative charge, and the areas shown here as the positive charge corresponds to the time when the capacitor is regaining its voltage. Charge balance simply indicates that the negative charge during a part of the cycle has to be equal to the positive charge during other part of the cycle, so that over one cycle there is no net accumulation of charge or net accumulation of voltage across the capacitor. This property is a dual property to what we see in an inductor. In an inductor which is working in an AC circuit, in a periodic circuit where the current follows a periodic waveform, I of t is I of t plus capital T, where capital T is the periodicity of the circuit. In such a circuit, from one cycle to the next cycle, there is no net accumulation of current. There is no net change in current, and this can be expressed in this integral equation 1 by L integral t to t plus t. Over one cycle, the voltage applied to the inductor, volt seconds applied to the inductor is 0. The volt second applied to the inductor is what is responsible for the flux accumulation in an inductor. So, what this indicates, in a periodic circuit, from cycle to cycle, there is no net flux accumulation, or net flux accumulation in per cycle is 0. This is also referred to as volt second balance in an inductor. This is a dual property of charge balance in a capacitor when it is excited by a periodic circuit and steady state is reached. Now, we come back to the same charge accumulation property. It is possible to express V as an initial voltage plus the accumulated voltage. The accumulated voltage is the charge that is supplied to the capacitor divided by the value of the capacitance. We can say that the capacitor stores energy by accumulating charge. As more and more charge is accumulated in the capacitor, more and more energy is stored, and this relationship is given by 1/2 of CV square. If a capacitor of value C is charged to a voltage of V, then the stored energy is 1/2 of CV square, and this is the relationship between the stored energy and the capacitor voltage. The capacitors normally are not designed by power electronics engineers for any specific application, but they are selected from manufacturer's catalog depending on what the value of capacitance needed, the voltage it has to withstand, the amount of energy it has to store, and so on. We will see some of those points here. The construction of a capacitor consists of one terminal, as you see here. Conceptually, it can be seen as terminal 1 and terminal 2, and in between a dielectric material is placed, and this configuration is capable of storing charge, and on account of this stored charge can store energy also. So, in this configuration of capacitor, it is possible to charge these terminals. Top terminal can be charged with respect to the bottom terminal, On account of the charges that are going to stay on the plates, there will be an electric field introduced in the dielectric material. That electric field is what we see here as capital E. This epsilon is the material property of the dielectric material. It is called the permittivity of the dielectric material, and D is the electric flux density. The electric flux density that is set up in the dielectric material is the product of the permittivity of the material and the electric field density, field intensity that has been established. This equation is also a complete analog to the magnetic flux density being equal to permeability time multiplied by the magnetic field intensity. We had seen that relationship when we were studying about the inductors. This is the relationship which relates the electric flux density to the electric field intensity through the permittivity of the dielectric material. Now, the electrical flux density is defined as in a symmetric circuit of this nature, whatever is the total charge on the terminals divided by the area of cross section of this dielectric material will give us the electric flux density epsilon times, and electrical field intensity is the voltage across the terminal divided by the distance between the terminals. So, I have written the same equation in terms of charge and voltage, and this gives rise to the relationship that Q by V is C, which is how capacitance is defined. Capacitance is defined as charge per volt in an electrical circuit configuration. The amount of charge that can be held in relation to the voltage that is built up on the capacitor. Charge per volt is the definition of capacitance, and this is also related through the dimensions of the capacitor and the property of the dielectric material. The area of cross section of the electrical field and the distance between the plates of the electrical field and the permittivity of the dielectric material decides what will be the capacitance value, epsilon times area of cross section divided by D. This is a relationship which relates the capacitance. This also is very similar to the way inductance is defined through the geometrical properties of N square by reluctance. We had seen in the earlier relationship. This relates capacitance to the dimensions of the electrical field circuit. Now, here what we see is the total energy that is stored in that. This can be very easily worked out as the work done in order to separate the charge through the potential. We have a total charge of Q from the negative plate to the positive plate, and the voltage across the plate is V. So, if you take a charge from this end and take it all the way down to the bottom plate, or a charge which is from the bottom plate pulled out and brought to this configuration, the work done is the energy that is required in order to move these charges through a field voltage of V. Q into dV integrated over 0 to V is the total energy stored, and this Q itself is C into V, and this gives rise to the famous relationship that the energy stored in a capacitor is half CV square. And if we substitute these numbers, very interesting results come here. We can see that the energy stored in a capacitor is the electrical field intensity, permittivity of the material, and the volume of the capacitor, the area of cross section and the distance of separation. So, if you try to find out what is the specific energy storage in a capacitor, that is per meter cube of volume, how much energy can be stored? That number is nothing but 0.5 epsilon E square. Energy density is 0.5 epsilon, permittivity of the material, and the electrical field intensity that can be established. In the case of air, if we wish to store energy in air, it is possible to set up a capacitor where air is the dielectric material. The dielectric material air has permittivity which is the same as free space permittivity, 8.854 10 power minus 12 farad per meter, and air can withstand a voltage a field intensity as high as 3 megavolt per meter or 3 kilovolt per millimeter. So, from this it is possible to see that in air it is possible to store energy with a specific energy density of about 40 joules per meter cube. If you work out this number, 40 joule per meter cube is a very small number. If you convert it into calories, about 4 joule is 1 calorie. So, this is equivalent to about 10 calorie per meter cube. 10 calorie is just the energy required to raise 10 gram of water through 1 degree centigrade or 1 gram through 10 degree centigrade, and you can imagine that it is not a lot of energy. It is a very small amount of energy. So, in air the maximum amount of energy one can store is not very high. On the other hand, if we use dielectric materials which are special materials, for example, polyester is one of the widely used dielectric materials, and in this particular material the energy density can go as high as 1.34 megajoule per meter cube. This is almost 10 power 6 times higher than what can be stored in the air. This is because the field intensity that you can set up is almost 200-300 times more, and the permittivity is about 3 to 4 times more. The relative permittivity of polyester sheet is about 3 or 4. I have taken 4 here. So, if we plug in these numbers, the energy density that you can get from capacitors is of the order of 1.3 megajoule per meter cube. And this is from a data sheet of a particular capacitor. It is possible to find out the dimensions here. For example, we see that the height of this is about 248 millimeter and the diameter is about 85 millimeter. And if we find out what is this volume, and for this capacitor if we calculate CV square, we know the voltage rating and also the capacitance value, and this capacitor is capable of storing about 65 joules and it has a volume of 0.7 meter cube, or the energy density is of the order of about 0.94 or 1 kilojoule per meter cube. So, commercially available capacitors invariably will have power densities of this order, about 1 kilojoule, even though theoretically the maximum possible will be of the order of megajoule per meter cube. Commercially available capacitors are almost 1000 times less. This is because one is required to handle the heat produced inside, and then the volume is not fully efficiently utilized and so on. So, roughly you can remember easily, it is 1 kilojoule per meter cube is a typical energy density of many of the bipolar capacitors. Against this, we also have electrolytic capacitors which are unipolar. They can withstand only one polarity of voltage, and such capacitors, what we see here as in the data sheet, these capacitors have the foil terminals and an electrolyte in between, and some process which increases the effective area of cross section of the dielectric material, which in effect gives rise to a power density of the order of about 6 kilojoule per meter cube, or you can roughly take it as almost 10 times more than what can be obtained in a bipolar capacitors. Electrolytic capacitors typically may have about 10 kilojoule per meter cube, and bipolar capacitors will have about 1 kilojoule per meter cube, and theoretically possible energy densities are much higher than that, easily 1000 times higher than this. The construction of a capacitor or the packaging of a capacitor is in more or less in a geometry which is cylindrical. We had seen both these capacitors which are bipolar and also the electrolytic capacitors which are unipolar have a cylindrical geometry, and the cylindrical geometry is obtained by winding two terminals in the form of a cylinder with a dielectric material which is in between, and this is rolled and obtained in the form of a cylindrical geometry, and with this cylindrical geometry it is packaged inside appropriate cans with insulations and so on. This is the preferred or the prevailing geometry which is used for capacitors which are used in most power electronic applications. There are several types of capacitors in the market. The simplest classification is between DC and AC, bipolar and unipolar, electrolytic and non-electrolytic. There are also some modern capacitors which are going by the name of ultra capacitors or super capacitors. They follow a different mechanism of storing energy that is not in the scope of what we are going to see now, but it is good to remember that we have emerging capacitors which are called ultra capacitors, which store energies which have energy densities which are easily orders of magnitude more than the electrolytic capacitors. Electrolytic capacitors have an energy density more than the metallized dielectric capacitors. The ultra capacitors have even better than electrolytic capacitors. The capacitors are specified by their voltage rating and the farad value. The unit for capacitance is farad. When 1 coulomb of charge gives rise to voltage difference between the terminals of 1 volt, that capacitance is defined as having a value of 1 farad. Q is C into V. Charge is the product of C into V, or C is Q by V, charge per volt. The two quantities which specify the capacitors are the voltage rating and the farad rating. And unlike inductors or many other electronic elements, the capacitors many times suffer from limited life, especially electrolytic capacitors have limited life. Typically, it could be about 8000 hours at 105 degrees, and if the temperature is reduced, it is possible to have more number of hours of life. For example, here is a data sheet for capacitors, and you can see that what you see here is the life characteristics. When the specifications are as given in the data sheet, one is 1.0 normalized specification at a temperature of 105 degrees gives a life of 8000 hours. So, typically 8000 hours is about 1 year of continuous operation, 1 year of life, and that is a satisfactory number. And if we operate at 60 degrees or 40 degrees, it is possible to get higher lives, 100,000 or 200,000 and so on. In a real capacitor, other than the voltage rating and the capacitance farads, there are a number of other non-ideal quantities that are involved, and what I have shown here are 3 non-idealities associated with capacitors. One of them is called the equivalent series resistance, ESR. Another one is called the equivalent series inductance, ESL, and the third one is the leakage current, I leakage. In a capacitor, under DC excitation, there should be ideally no current flowing from the positive to the negative terminal. The current through a capacitor for DC has to be 0. But in a real capacitor, on account of the ohmic leakage paths between the electrodes through the dielectric or through the surface of the dielectric, there is some small leakage current flowing, and that is one of the non-idealities in the capacitor, a small leakage current. Another non-ideality is that because the current is passing through a conductor and led to the terminals, and similarly from the other terminal taken to the other plate of the capacitor taken to the terminal, it is necessary to establish a current path from the terminals into the capacitor, and we know that every current path has an associated magnetic field, and on account of that every current path will also have an associated equivalent inductance. This series inductance, which is known as ESL, is associated with the conducting path of that, and in the same way every conducting path when current is flowing will result in a voltage drop proportional to the current, and that part of the non-ideality we call it as equivalent series resistance. For example, if you take the capacitor specification of this one, you can see that there is a self inductance which is the same as LESL 180 nanohenry, and it has a series resistance RS shown here as 1.4 milliohm. So, this ESL and ESR or the series resistance and the self inductance are the non-idealities that is associated with every capacitor. If we look at the data sheet of the electrolytic capacitor, it is possible to see that as at 20 degrees centigrade there is a leakage current associated with the capacitor, which is not very high, but it is there. It is about microamperes, 4 microamperes multiplied by a variable quantity which is proportional to the capacitance value. Okay. And the ESL is also given for this self inductance LESL for different packages, 14 nanohenry or 18 nanohenry. And in the same way, you will see that there is an associated ESR also at 100 hertz at 20 degrees. Most of these capacitors have certain milliohms. What you see here in this column, 5300 microfarad capacitor, which is rated for 350 volt DC, has an equivalent series resistance at 20 degrees centigrade, which is 16 milliohms. These are small resistances, but certainly they are there, and associated with that there will be losses also. The consequence of this ESR is the loss in the capacitor on account of the current that is flowing, the AC current or the ripple current that flows into the capacitor, and this ESR produce a power loss which is I square into ESR resistance. This loss is also going to result in temperature rise inside the capacitor. If the capacitor has certain thermal resistance which is in degree centigrade per watt, and depending on how much power is dissipated on account of this ESR, the power dissipation multiplied by the thermal resistance will result in the temperature rise of the dielectric material inside the capacitor, and if this temperature rise is too high, then the capacitor will fail. So, it is necessary therefore to make sure that we do not dissipate more power than what is safe for that. Let us see in this data sheet, probably we will see the power dissipation limits. So, you can see here in this particular data sheet the ambient temperature on one side and the power dissipation on the other side. So, this capacitor, it is possible to dissipate about 9 watts of power at an ambient temperature of 20 degrees centigrade, and at an ambient of 45 degrees the power dissipation can be only 5 watts, and at an ambient of 85 degrees you cannot dissipate any power at all. So, this line is the power dissipation characteristics for natural cooling. So, what you see here on this side is for natural cooling, and if you use fan for forced cooling, it is possible to dissipate more power in the capacitor, and the kind of relationship is what we had seen, that the temperature rise is related to the thermal resistance multiplied by the power dissipation in the capacitor. The ESL has a different consequence in the capacitor. On account of the self-inductance, the capacitor and the self-inductance can form a resonant circuit, and this resonant frequency is 1 by 2 pi root C into L, this product. So, on account of this inductance, you will find that as you go to higher and higher frequencies, there is a resonance in the circuit which can give rise to damage to the capacitor, or if you go beyond the resonant frequency, the complete element will behave only like an inductance, and these are also bad things. If you try to use a capacitance at too high a frequency, the ESL will not allow that capacitor to function purely as a capacitance, and it will have a number of side effects which are not very advantageous. The leakage current can be shown as a shunt loss. Normally the loss is not very heavy. We will see later what is the more major consequence of this leakage current. So, these are the three major non-idealities: equivalent series resistance, equivalent series inductance and the leakage current. We come back to the same kind of waveform. It is possible to work out the numbers, convert this voltage waveform into the appropriate current. If the capacitance is 100 microfarad, a 800 volt rise in a time of 1 millisecond will give rise to a current here at this point, which will be C into dV by dt. dV by dt is 800 volt per millisecond multiplied by 100 microfarad will give us a current which is about 80 amperes positive. And during the time here the current is 0, and similarly during the fall time the current is minus 80 amperes because the current is falling down. And if you come to the next section where the current is sinusoidally changing, the voltage is sinusoidally changing, the current is now a cosine. The peak I have taken as minus 80 amperes. So, we can work backwards to find out what will be this maximum voltage. And we see that voltage is the maximum voltage accumulated on the capacitor is nothing but the charge that is accumulated on the capacitor from this instant to this instant, which is 1/2 of this sine time, which is about 1.25 milliseconds. So, in a time of 0 to 1.25 millisecond, how much is the charge, which is the area of this figure? That area can be mathematically calculated, 80 cos omega t dt integrated from 0 to 1.25 millisecond and divided by the capacitance value, and this number is 637 volts. So, what we see is that the voltage accumulated in the capacitor for this current is 637, and then during the next portion the current reverses and this 637 is lost and the voltage across the capacitor comes back to 0 and continues till the end of the cycle. After that the cycle repeats. So, in this particular situation we can find out what is the dissipation in the capacitor by finding out all the RMS currents and multiplying it by the ESR. ESR of this capacitor is 1.4 milliohms, and that has to be multiplied by the RMS over one cycle, over 8 millisecond cycle. We find out RMS contribution on account of the current here. This must be 80 amperes, 80 and minus 80. 80 square into 0.125, 1/8 of the cycle, 80 square into 1/8 of the cycle. Then this sinusoidal one, if it is a pure cosine or sine, it will be 80 square into 0.5, it will be the RMS square, but this is only over a period of 2.5 millisecond, which is 0.31 times 8 millisecond. So, this quantity now turns out to be 80 square into 0.41, that is the I square RMS, that multiplied by the equivalent series resistance gives a power dissipation of about 3.67 watts. So, for this particular capacitor, the power dissipation can be as high as 9 watts or 20 degrees or about 5 watts at 45 degrees, and the dissipation that we see here in this example is about 3.67 watts, and that is not a very bad thing. We are well within the limits of the dissipation of this particular capacitor, and this is the way one goes about finding out how much power dissipation takes place in a capacitor. How do we measure a capacitor? The measurement of a capacitor can be done following the same kind of relationship. Current is C dV by dt. So, if we apply a current to charge the capacitor and discharge the capacitor, a constant current will give rise to a charge in the capacitor which linearly increases, reaches some peak, and a negative current will discharge the capacitor back all the way to 0. So, if it is possible to set up a circuit in order to charge a capacitor with known amount of current for a known duration and measure the voltage across the capacitor, then using this relationship of I is C into dV by dt, it is possible to measure the capacitance. See, many times this will be very necessary to measure the value of the capacitance. The reason is the value of capacitance as given in the circuit. Let us go back and see some of the data sheets, and we will see that. So, we said that this is one simple way of evaluating the capacitance by supplying some current and finding out in a known time how much voltage has been picked up. Yeah, typical capacitance values change by as much as plus minus 30%. If you buy a 1000 microfarad capacitor, it could be anywhere between 700 microfarad to 1300 microfarad, because the manufacturing processes are not very well controlled or stable. The typical tolerance on the value of capacitance can be plus or minus 20%, and so it may be necessary that in many cases, even though you know the value given on the label, it is better to cross check and see what is the value of the capacitance, and a circuit of this nature can help us to measure the capacitance. There is also another way of measuring the capacitance, which is the measurement through LCR meter. Just like the inductors which are used for which are measured with LCR meters, capacitor measurement using LCR meter uses the principle of sinusoidal excitation. You supply a certain high frequency voltage to the capacitor and measure the current flowing through that, which is at 90 degrees. Now, this process of measurement normally will work with some small amount of current and at a different frequency. In many cases, the frequency can be different from the frequency at which we use the circuit and so on. So, the measurement of C with an LCR meter, even though it is useful, it is not a very dependable number. It will give a number which is the small signal capacitance, not the kind of charge by V at the operating conditions. So, it will be better to make the measurements following this method when you are in doubt. Okay. The LCR meter is one method of making the measurements. Just in the case of an inductance, a capacitance also can be seen as an impedance, and we see that the capacitive impedance V by I, it must be 1 by j omega c. Okay, this is not j omega L, it must be 1 by j omega c, and as a function of frequency, the capacitance keeps dropping. If it is capacitance, the impedance is 1 by j omega c, and it keeps dropping with frequency with a slope of 20 dB per decade. Drop is minus 20 dB per decade, and the frequency at which the impedance is 1 ohm will be omega equal to 1 by c. This is the impedance plot dB ohm versus log omega. We had seen a similar kind of curve for inductance. This would be the ideal impedance curve for a capacitance. When we have a network analyzer, it is possible to measure the impedance as a function of omega and then also find out the value of capacitance. Let us look at a typical capacitance that we had seen here. We saw the data sheet of this capacitor. It has 180 nanohenry as the self inductance, 1.4 milliohm as the resistance, and 100 microfarad as the capacitance. And those are the numbers that we see here. RESR is 1.4 milliohm, LESL is 180 nanohenry, the capacitance is 100 microfarad, and if you calculate the natural frequency with these values of L and C, it is about 235 kiloradian per second, 1 by 2 pi root of L and C, and that frequency is 235.7, and the unit for that is kiloradian per second. Now, if we plot this as a function of frequency, you can see that at very low frequencies, this is an open circuit, because the capacitance is an open circuit at low frequency, and so you will find as you go to lower frequency, the impedance goes to infinity. But at the lower end, this behaves like a capacitance. So, with increase in frequency, impedance keeps falling, and this fall is with minus 20 dB per decade, the slope of this. And where this goes through 1 dB ohm, that is 0 dB ohm, which is equal to 1 ohm, is when omega is 1 by C. And in this particular case, C is 100 microfarad. So, 1 by C is 10 kiloradian per second. So, at an angular frequency of 10 kiloradian per second, this capacitance has an impedance of 1 ohm. And on the other hand, when you go to very high frequency, this behaves like an inductance, and this capacitance being a short and this RESL being a very small 1.4 milliohm, this behaves like an inductor, and you see that the high frequency impedance is increasing with frequency with plus 20 dB per decade. And again, the 1 ohm impedance on this part of the characteristics is when 1 by L is the impedance. L is 180 nanohenry in this particular example. 1 by 180 nanohenry is 5.56 megaradian per second. So, at that frequency also the impedance is 1 ohm. At 10 kiloradian per second also it is 1 ohm. At this frequency the capacitance is contributing to the impedance and the inductance is practically short circuit. And at this frequency the inductance is contributing to the impedance and the capacitance is a short circuit. And in between 1 by root LC, which is the natural frequency 235.7 kiloradian per second, which is the resonant frequency of this capacitance, that is when the circuit resonates and the impedance becomes minimum. The inductive reactance and the capacitive reactance cancel each other, and the terminal impedance is just RESR, which is 1.4 milliohm. So, if you now plot the terminal impedance of this device, which consists of a resistance, a capacitance and an inductance, it will be falling linearly at minus 20 dB per decade, passing through 1 ohm at 10 kiloradian per second, and then reaching a resonance or the minimum frequency at 235.7 kiloradian per second, having a value of 1.4 milliohm. And as you go to still higher frequencies, impedance keeps increasing because of this inductance, and at 5.56 megaradian per second, this reaches again 1 ohm and then it keeps increasing. Now, if you see this curve, it is very easy to see that at the low frequency, the impedance behaves like a capacitance. At high frequency, the impedance behaves like an inductance, and there is a resonance in between. There is a resonance at this natural frequency. Now, it is possible to now identify a region where the capacitive impedance as calculated by 1 by omega C and as seen from this composite element are very nearly equal. At any other point, see, ideal capacitor will have a capacitance which is falling linearly all the way down, but you can see that the impedance of this, what we see here, and the ideal 100 microfarad capacitor are very nearly the same with respect to each other, only in this frequency range. I have marked a circle here. So, probably up to a frequency of somewhere between 10 kiloradian and 235 kiloradian, we might probably take it as somewhere around 100 kiloradian. Only in that range, this is a satisfactory capacitor. Beyond that range, the non-idealities become dominant and they do not allow you to use this capacitor successfully. So, this impedance curve is a very powerful method of finding out what is the useful range of a capacitor, useful range of operation. Now, there are a few safety features one has to worry when using capacitors, because the capacitors hold charge and this charge holding can be forever, because the leakage current being so small, this discharge time constant of a typical capacitance is about 10,000 seconds. It is almost 3 hours. So, even after you have removed a capacitor from a circuit, even 3 hours after you have removed the capacitor, you might still have about 30% of the charge left on the capacitor. And if without meaning to, unintentionally, if you short circuit the terminals, it can give rise to a big spark and a fire accident. So, you can see that this MKV capacitor has a time constant which is of the order of Rs into C is greater than 10,000 seconds. What you see, the bottommost line Yeah, this is the bottommost line. That it has a time constant of 10,000 seconds, which is what is equal to about 3 hours. So, it is very necessary that one has to be very safe while working with capacitors. Even when the circuit is not connected, it is possible that capacitors may be carrying charge because of what they had taken while they were previously energized. So, it is necessary to wait for sufficiently long time or have appropriate circuits to discharge the energy in the capacitor. This is a very important safety precaution while you are working with capacitors. Many times you may buy capacitors from the market and your voltage rating may not match with what you want, and it may be necessary to operate these capacitors in series in order to obtain higher voltage ratings. You can easily obtain higher voltage rating by connecting the capacitors in series. All that one has to take care is that the voltage sharing between the capacitors is proper. Now, for that purpose, it is necessary to use resistors across the capacitors known as bleeder resistors. Normally, we will use a bleeder resistor which will draw a current through them, which will be a few times more than the internal leakage resistance. So, that the voltage division is now decided more by the bleeder resistor and not by the internal leakage resistance. And this is one way of ensuring that the capacitors share the voltage properly, and this is an additional loss in the circuit. On account of the bleeder resistor, you will have additional losses. A typical electrolytic capacitor we had seen had let me see the current, how much was the leakage current. You saw that leakage current of the order of 4 microamperes plus some number. So, invariably this 4 microampere is a more dominant quantity. When the capacitor value and its microfarad, rated voltage and the operating voltage, all these are fitted in, probably leakage current will be very close to 4 microamperes or maybe a little more than that. Okay. This is a small current. Because it is a very small current, this can give rise to large unbalance in the voltage that is shared when they are using in series. So, on account of that, it is necessary to use what are known as bleeder resistors across the capacitors to make sure that voltage sharing is proper. In the same way, if you are using capacitors for large current applications, it is necessary to connect several of them in parallel. A single capacitor may be capable of taking only about 40 or 50 amperes of RMS current, and if our application demands 500 amperes of RMS current, we may have to connect several of them in parallel in order to reach the requirement. When capacitors are connected in parallel, one more precaution essential is that the high frequency currents are now going to be decided by the ESR values. So, the ESR values as per the catalog may be equal, but if your connection has non-ideal contact resistances or the conductor resistances, it is necessary to make sure that those paths are also identical. For example, if you connect an external connection coming from here to the capacitor back here and then next capacitor is connected from here to here, you will find that for the external current that is coming from the left hand side, the first capacitor RESR is only what is given in the data sheet, but for the second capacitor, it is a capacitor resistance plus the track resistance here plus the track resistance here. This can give rise to problems. So, that is the reason when you connect them in parallel, it is necessary that the physical layout has to be done so that the symmetry is not lost. For example, we will feed in from this point and feed out from this point. So, this parasitic resistance and this parasitic resistance, one will come in series with this capacitor, one will come in series with this capacitor, so that both of them are equal. Okay. Yeah, we have seen most of what is needed for capacitors, and with this we have seen the devices that are essential for power converters, and from here we will move on and then in the next few lectures try to cover some problem sets covering all these material, and then go on to circuits which use the devices in order to carry out the function of power conversion. Thank you very much.